All right, I'm going to start the lecture. Oh, is the recorder on? Did I turn on the recorder? Was anyone paying attention? Yes, the recorder was on. Okay, so it has been on. All right, so I have graded 3 out of the 5 questions, except for people who took the test early. Um, so I still have 2 more questions to grade, the last 2 questions, basically. So the way I do grading is I grade 1 question for the entire class, which is mind-numbingly, it's a mind-numbing experience. I'll just put it very kindly. But it's the best way to do it because this way I can stay consistent when I move from one student to another student, so I can apply exactly the same standard to the entire class. So that's why we are you're only seeing 3 of the questions being graded. So other than that, are there any questions about the exam? Yes? I will, as soon as I find time, I will do it. So each question takes about an hour and a half to grade. No, for this class it's close to 2 because I have like 60 plus copies to grade in this class. So depending on the question, some questions was really difficult to grade. Like the first one was really hard to grade because different people do it slightly differently. Now, if everybody did it correctly, like 100%, it would make it very easy. If everybody got it wrong 100%, it would make it very easy. But most people do it like mostly right or partially right. That makes it kind of difficult for me because I have to then evaluate and go like, okay, it's not going to be 100%, it's not going to be 0%, but there are a lot of percentages in between, right? So that makes it kind of difficult. So multiple choice tests would kind of eliminate that particular factor, but I found many, many years ago that there are a lot of people who can score really high in multiple choice tests, but they really do not understand the subject matter. So I cannot use multiple choice tests in classes like this. So is that kind of answering your question? All right. So getting back to the lecture material of this class, I'm hoping you guys still remember what we talked about before the break, before the exam. We were talking about how to use the stack. We talked about calling and returning already, and we talked about how to return a value. So remind me, how do we return a value? What is the convention that I use in this class so that a subroutine can return a scalar value to the caller? Through register A, exactly. So when a subroutine returns, whatever in register A is the return value. What if a subroutine has no return value? What if it's a void function? Then we ignore whatever is in register A. The caller will simply say, I don't care what is in register A. It has no special meaning. On the other hand, if you have a subroutine that returns an integer, then the caller, after the subroutine returns, the caller will look at register A and say, oh, whatever is in register A is the return value. And it will treat it as such. Is that okay? So do you still remember that portion of the lecture, like on the Tuesday before the exam? Yes? Hopefully? Okay. All right. So I'm just going to point out where we are in terms of the material and also what is going to be the lab activity for tonight. So the lab activity for tonight is parameters and return value. So that's going to be what we'll be focusing on for this particular class, is how do we pass parameters, which we also kind of touched on the Tuesday before the break. So how do we pass parameters? What kind of construct do we use to pass parameters? We push it on the stack. We push all the parameters on the stack. Very good. So that means we can take a look at some sample programs. So let's go ahead and take a look at a C program. And since it talks about parameters and return values, we'll start with something simple, okay? We'll start with something that looks like this. uint8_t, which means it returns an unsigned 8-bit integer, and it has a name of 5. And all it does is to return the constant value of 5. This is a C subroutine, and I'm hoping that all of you know what it is going to do as a C subroutine. So are there any questions about what it does in C? No. Okay, very good. So the next thing we do is we say, okay, well, how do we implement this in assembly? So we opened up another window, and I'll do it side by side, so this way you can look at the C code and you can look at the assembly code. So in assembly code, we're going to start with 5 as a label. So 5 as a label in assembly language is simply the symbolic name of the entry point of the subroutine. So what you know as a function name in C and C++ and most other programming languages is no more than just a symbol to basically say, yep, here's the starting point of the subroutine. 5 colon in assembly is doing the same thing. It's a symbolic name of the entry point of the subroutine. So you guys already told me that to return a value of 5, we just have to put that value into register A. That's all it does, okay? So line 2 of the assembly code is basically corresponding to line 3 of the C code with one minor caveat, okay? The caveat is in C and C++ and most modern programming languages, the return statement actually it has 2 things to do. The first thing is to specify the return value. The second thing is actually to return to the caller. Okay? So now in assembly, we also have to say, okay, how do we return to the caller? Well, this brings up another agreement between the caller and the callee, the subroutine that is being called. What do you think the stack pointer should be pointing at when we are at the entry point of the subroutine? What was the last thing that we pushed on the stack from the caller's perspective? Yep. Yep. So the stack pointer is assumed to be pointing at the return address. And what is our stack pointer? It's just a convention. Remember, we talked about this. It is just a convention that I use a particular register as our stack pointer. Which register did I use? Yes? Register D. Very good. Okay. So that means if I do something like this, then register B will now have the return address. In other words, if we can somehow get back to whatever register B is pointing to, we have successfully returned to the caller. Okay? So that means, now don't copy this, because I know you guys are going to do it anyway. So this will do it, right? JMPB is basically saying the same thing as PC equals B. Okay? Whatever is in register B is copied to the program counter. And what is the significance of the program counter? What does it do in the processor? What is its job? It specifies where do we fetch the next opcode in RAM. So if I change the program counter directly, I'm changing the path of execution directly. Is that okay? But I'm missing one thing here. Because as a stack, once you make use of something and it has no value after this point, we have to get rid of it on the stack. But there's no such thing as removing a memory location other than using a laser and burn some transistors in your RAM module. Okay? We don't want to do that. Okay? So what we are going to do instead is we are just going to increment the stack pointer. Incrementing the stack pointer basically says, because what the stack pointer is really doing is it's a bookmark. Okay? So consider the stack as your notebook. Okay? And you have a bookmark that is the stack pointer. It says everything after the bookmark is in use. Everything before the bookmark is free. That's what the bookmark is saying. So just by moving the bookmark one page to the back of your notebook, I am now done with quote unquote deallocating that page. Did I destroy that page? Did I tear that page out and put it into the recycle bin? Nope. Did I erase the content of that page? Nope. I did not do a single thing about what is on that page. I just moved the bookmark, which is a very inexpensive operation because it just involves changing a single register and just increment it by 1. Okay? So that is how we implement the subroutine 5. Okay? So do we have any questions about the implementation of 5 as a subroutine? Is that good so far? Yep.
I had a question about the instructions versus the stack. What happens when you get to the very end of the instructions, but the very beginning of the stack? What stops it from overwriting the instructions?
That is a very good question. So the question is, since we are assuming the stack starts from the location 255 and it works its way down to earlier or lower memory addresses, and we write the code to increasing addresses, so at some point they're going to meet. And you're correct. Bad things will happen when they do meet. And typically what happens is the stack is going to overwrite locations that have legitimate opcode in it. So the program is going to corrupt itself. And just really bad things will happen. And that is basically what earlier computers have had to deal with. So if you go all the way back in time and look at the Commodore 64, the Apple II computers, the TRS-80 computers and whatnot, because they do not have a protected mode to operate on, so there's no way to prevent the stack from stepping into the program space. And as a result, if your program is not written correctly or you did not estimate how much stack space is actually needed, you do end up with problems like that. And it's unavoidable. Now, modern operating systems are not like that. Okay? If you write a recursive program, okay, if you're taking cisp310, you have to deal with tree structures and many other recursive subroutines. And trust me, okay, I have done it several times. You end up with an endless recursion. You run out of stack, and guess what? The program just dies, right? But your operating system is fine. It's just one program dies. We're having a segmentation fault in Unix or Linux, and in Windows, I think it's called what is it called in Windows? Exception. Exception, very good. So it's an exception in Windows. It's just the same thing, but reported differently. It's termed differently between the two operating systems. And that's because modern operating systems like Linux, Mac OS X, Windows, and so on, they are all protected mode operating systems where they can set the boundary and say, okay, stack is only from here to here. If you go beyond this range and try to access memory out of this range, I'll give you a segmentation fault. Okay? Now, segmentation fault itself, by itself, is not a bad thing. Okay? By itself, it simply means we're trying to access memory that is not there. Now, this goes to virtual memory, which is way beyond the scope of this class. But it's just a way of your application program telling the operating system, it go like, well, operating system, we are running out of space here. Can you allocate more memory so that I actually have some actual locations to access? But if the operating system says, nope, you're supposed to get 1 megabyte as your stack, and you have used it all up, I'm not going to allocate any additional space for you, then the program will crash. Okay? So there are a lot of things happening behind the scenes that we do not see because of virtual memory, but that's a different topic, not for this class. When I took the equivalence of this class at San Francisco State University, the professor actually went in and talked about virtual memory organization, how page faults happens and all kinds of stuff like that. So, but you guys got to talk about, the carry look ahead adder and stuff like that, which I did not learn until much later. Yep.
Does LDI A5 return the 5 as an address in the RAM or as content?
Well, what does it do? What do you think the LDI A,5 opcode, what do you think it does?
It stores 5
Exactly. And that's all it's going to do.
So does it store like the address of 5,
What is the address of 5?
address number 5 in RAM, or the content in address number 5?
It has no address. It's a constant. 5 is just a value. Now, you can store 5 in a memory location if you want to. So if you have a local variable and you say x equals 5, then 5 is stored to the location that you have allocated for that local variable x. You can do that. You can also do something like this and store the value of 5 into a register. So it is in a register, and that's all the subroutine is going to do. Because the subroutine has no idea what the caller is going to do about the return value, right? Okay, so are we good with 5 or not? We good? Okay. So we'll write another subroutine then. We'll write another subroutine. We'll call it double. And double doesn't do anything too exciting either, because all it does is to say return x plus x. Okay? So we want to know how this is going to be done. So we shift to the assembly code, and we say, okay, fine, we can define double as the entry point. But now we have to understand what is on the stack at the entry point of the subroutine. At the entry point of the subroutine, we now have two things on the stack that is of importance to the subroutine. We know the return address is important because I need that in order to get back to the caller. But there's another thing that is also important on the stack. What is that? Yep. The parameter that is passed. Parameter x is also on the stack. So now the question is, where is it? Okay. I know they have to be in consecutive memory locations. Okay, it doesn't make sense that they are spaced out by some locations. Okay, but which one is at the higher address and which one is at the lower address? That becomes the question. So in order to answer the question, we have to get back to one of the assumptions, one of the agreements between the subroutine and the caller of the subroutine. The stack pointer at the entry point of the subroutine, the stack pointer always points to the return address. So where do you think the parameter is? You only got two choices, right? It's either right above or right below. Which one is it? It cannot be below, because anything below where the stack pointer is pointing to is unallocated. That space is not being used. It is above. Okay? So what your stack is going to look like is this. Okay? You have parameter x, and then you have the return address right below it. Yep.
Sorry, when you're saying above and below, like is above like if you're at 254?
Okay, I'll write it this way to make it more clear. Whatever D is pointing to is the return address, and then whatever D plus 1 is pointing to is the parameter x. Double equal it, because I'm not changing it, I'm only stating what is there. So is that notation okay? D is register D, by the way, which is also known as the stack pointer in this context. So are we okay so far? Okay. So in the subroutine, we are not really worried about returning yet, because that's the last thing that we have to do. What is the first thing that we need to do? If you just look at the C code, don't look at the assembly code, look at the C code, look at line 8. What do we need to do first on line 8? We need to figure out what x is, right? But in order to figure out what the value of x is, what do we need first? We need to know its address. Okay? So our first issue, or the first thing we need to do, is to find out what is the address of x. Now, this is one of the things where the conversion from C code into assembly code can get tricky because of the way C code works. When you look at C code, x is easy to get to. The address of x takes some extra work, or so it would seem, right? because the symbol or the expression of the address of x is ampersand x, right? So it seems to us, okay, from the notation, that it's easier to get to the value of a local variable than it is to get to the address of a local variable, just because we have to add that operator ampersand. Is that okay? So most people would have that association, okay? I can get to the value first, okay? But sometimes if we need to, we can get to the address. But in assembly code, it is exactly the opposite. You cannot get to the value of something until you know where it is. So you always have to get to the address first. If the address is all you need, cool. But most of the time, it is not the address that you want. It is the value that you want. So it's an extra step to get to the value. So keep that in mind when you're working with anything that is on the stack, except for the return value. Okay? All right. So the first thing we need to do is to somehow find the value of, find the address first of x. So you might say, oh, but this is it, right? So can't we do something like this so that we end up with a being whatever is at d plus 1? The answer is no. You cannot do this. Why not? Because it seems to us that parentheses in assembly code means dereference, right? So instead of dereferencing just D, I can dereference whatever D has and then plus 1 to it. Nope, cannot do it. Why not? Because the way the assembler works is it looks at LD and figure out which family of opcode we're dealing with. Okay, do you guys remember the opcode table? Okay, let's think about this from the perspective of the assembler. Okay, because the best way to explain this is to look at things from the perspective of the assembler. Now, I'm not asking you guys to write your own assembler, okay? But I'm asking you to understand what it looks like from the assembler's perspective, okay? So what we'll do is we're switching gear and get back to the opcode table. Okay, so let's see what is the quickest way to get there. Okay, that we get to it pretty quickly. Now, if I could send that cricket out of the classroom, I would. I think the cricket is being very disruptive, right? It's distracting me and distracting you. I went to Southern California for a union trip, and guess what I had for dinner? Yep. To me, it's a little bit they put too much spice and salt in it, so I couldn't really quite taste the cricket. Huh? I like the taste of cricket. Thank you. I had a trip to, where is this class? It's spring. Okay, there we go. Okay. Oh, why am I doing this? I need to go to Google Drive. Okay. Went to the wrong place. And here we have the processor under shared. And the opcode table is what we need to look at. Okay, so from the assembler perspective, what it's going to do is it will extract the first word, which is LD, and it will go through a table to find out, okay, we got LD, which family of opcode does it belong to? So it will do the same thing as what I'm doing here, except with a lot better efficiency. So it will locate this particular row, and it will say that, okay, every single LD instruction is going to look like this. In hexadecimal, 7 something, okay? And then what it will do is it will look for which register is receiving, is being modified. Okay, what is my X register? So in the case of the assembly code that we were talking about, where is it? There we go. It's register A, right? So the assembler would now say, oh, register A is taking the place of X. And A is represented by 0, 0 in the register bank. So XX is now 0, 0. And then it will say, oh, I'm expecting open and close parentheses around the second register. And it will look back to my code and say, OK, I find the two parentheses. That's good. And then it will ask, what is inside the parentheses? And we can only have one single letter inside the parentheses. In this case, we have D plus 1. So now the assembler is going to be confused. It's like, I am only expecting one single letter. I'm not expecting something plus 1. So the assembler will fail to recognize this as a valid mnemonic. Sorry? Exactly. Well, yeah. But it will recognize this one. Even though it's not doing what we want it to do, it will recognize it. Because now it can say, oh, D is register Y, and D is, let's see, 0, 1, 2, 3. So it's 1, 1. So now we can, so the assembler will now assemble the opcode and say, OK, it is 7. And then we have 0, 0, 1, 1, which is 3. So 7, 3 is representing, is the underlying opcode, the binary opcode of LDAD in parentheses. That is the process that the assembler is going through to convert the mnemonic into opcode. So that is why you cannot have D plus 1 in it, or 1, or 5, or any label inside the parentheses, because it is specifically looking for A to D as a single letter. Is that OK? And that is what it needs in order to figure out, what do I use to fill up these 2 bits, YY? So is everybody kind of understanding from the perspective of the assembler why you have syntax requirements that you have to meet? Okay. All right. So now getting back to the translation of the code. All right. So we cannot do this. OK. So if we can't do this, what else can we do? Oh, what about this? What about I increment D first? Would that be a good idea? It's not a good idea. Now, the illustration of why this is not a good idea is kind of long. But you do not want to move the bookmark until you are really sure that you don't need that page anymore. Well, you can potentially be losing the return address. Yep. Hmm? No, you're not decreasing it either. Yep. Say again? Right. You have to make a copy of the register and then work with the copy of the register. But I want to explain why this is not a good idea, why you do not want to increment it first. Let's see. So it's going to take a little bit of a digression. I'm just evaluating whether today is a good day for that digression or whether I should save it for later. I think this is a good place for the digression. So let's do that digression. We'll get back to this, OK? I promise we'll get back to this. And it's recorded, right? So let's do this digression. The toy processor is not capable of interrupts, OK? But most processors are. So you have to write your code as if you're writing your code for a processor that is capable of doing interrupts. And you might ask, but why? Your processor doesn't do interrupts. Can't we just write code assuming there are no interrupts? No, you cannot, okay? Because my job here is not to prepare you to program using the toy processor, because that's not practical. No one is going to program in the toy processor after this class. But you might write code or what we call ISRs, interrupt surface routines, for the ARM processor. Why? Who do you think in the world is going to write code, assembly code, for the ARM processor? And by the way, why is it called the ARM processor, not the leg processor? What does ARM represent? There's a name, right? So what is in a name? And by the way, what is the significance of the ARM processor? Why is it a big deal? Yep. It runs all your phones. It runs all the anything that requires low power and has a complexity where a AVR processor cannot handle. It's probably ARM based. Your Raspberry Pis, those are all ARM based. Okay, if you look into a car managed navigation system or any type of embedded system inside the car, I would bet you that there's a good chance that it's also ARM based. Okay, so ARM is not the ARM architecture is not something that is unlikely that you will encounter. So we'll look up why it is called ARM. Oh, I think Wikipedia probably is the faster way to do it. Okay. And so here this is the name, why it's called ARM. It's called Advanced RISC Machine. Okay, originally, but now originally it's called Acorn RISC Machine, but now it's called originally, and now, what is the current explanation? Do you see anything? I guess they don't care anymore. Yep.
I think it's just called ARM now, and previously it was called Advanced RISC.
Well, previously it was the abbreviation of Acorn RISC Machine, and then it became Advanced RISC Machine, and now it's just ARM. I think they just thought that advanced is really silly, because once you have more advancement over advanced, do we call it AARM, and then AARM, and then AAARM? It's advanced RISC Machine. ARM. We can call it Ultra ARM, right? So anyway, this is inside every single phone. As far as I know, every single phone is based on it. And then somebody's going to complain and go, no, it's Snapdragon. But what do you think is Snapdragon? Shall we look it up? Okay. Cell phone Snapdragon. Okay. And we'll look up the Wikipedia entry. There we go. And I'm just going to look up the name ARM. And they're all ARM based. So inside the Snapdragon processor, each core is basically an ARM processor. It's an ARM core. So when you write code for any cell phone, okay, eventually it boils down to ARM instructions. Is that okay? So have we established that the ARM processor has significance? Okay. Next question. Who's going to write code in assembly now that we have C compilers? What do you think? Anyone? Yep.
People who want to optimize code.
Okay. What about code that cannot be expressed in C and C++? Do you think there are parts of an operating system where you cannot express what needs to be done using C and C++? Yep.
Maybe the people who are writing the compilers from C to
There are those people too, but there are also people who are very interested in interrupts, and at the same time they have to write code in assembly. Why do you think there are those people? I mean, which part of an operating system do you think requires assembly language programming, where C is not low level enough? There are a few pieces of code. The one is the bootstrap code. Okay? When you first power up your phone, okay, the code that runs does not even know where RAM is. It has to find it. So if there's no RAM, you cannot call functions, because calling functions require a stack. A stack can only live in RAM. So you have to write code in assembly, because C code simply does not work when you do not provide a stack. Okay? So the bootstrap or the firmware has to be written in assembly. Now, once you have found RAM, then you can actually write C code, because now you can say, okay, here's your stack, and then the compiler can just say, okay, I'm assuming that portion is the stack, and everything will work. But there are other things that you cannot express in C and C++. Okay? Interrupt surface routines handle those kinds of stuff. So what do you think, what kind of code is in an operating system requires that kind of low-level access? Anything that accesses the I/O devices, input-output devices. Now, what kind of I/O devices are we talking about? If you look at your phone, okay, what are the input and output devices of a phone? I mean, the phone has more I/O devices than a desktop computer. So, okay, touch screen, okay, that's an input-output device, okay? USB, input-output device. Microphone, speaker, the graphics, okay? The interface to the graphic processing unit, the GPU, okay? That's an input-output device from the perspective of the processor, okay? The radio is an input-output device, right? The Wi-Fi chipset is an input-output device. What else? Did I miss something?
Camera.
Camera, okay, very good. The camera is definitely an input-output device. And I missed two other things. GPS, compass, 3 other things, and the accelerometer. Those are all standard devices on just about any phone these days. So now the question is, well, what is so special about code to interact with that kind of stuff? Okay. So what I will do is I'm going to put you back in these days. Okay, so I'm going to use a picture to help you establish the context. So TRS-80, and we'll look at this computer. So imagine you're back in those eras, okay, and you're using this type of computer, and it's obviously it doesn't have a GUI, right? So without a GUI, how do you interact with the computer and say, I want to make a copy of this document? What do? You cannot just click on the file and then type Control-C and then Control-V somewhere. Doesn't work. So what do? Use a command line interface, right? Okay. And what is involved in this picture if you want to use a command line interface? Obviously the screen, right? What is the second part that you need? The keyboard. Okay. So now the operating system has to know what you're typing. And how does it know what you're typing? There's a controller, okay, a keyboard controller that can scan all the keys and figure out which one you have pressed. Okay, it can understand whether a key is pressed or depressed. Okay. And there's a dedicated processor to do that, so that your main processor doesn't have to keep scanning the keyboard to find out which key is pressed. So let's say you're writing the command line interface. You're writing a shell. Okay? What do you need to do to figure out what the user has typed? And I'm not even talking about parsing the command itself. I'm just talking about what is being typed and just put it on the display. That's all I want to do. So what do you need to do? You got two approaches. The first approach, which is the obvious one, is to keep asking the keyboard controller and say, do you have a key? The keyboard controller says, nope. Do you have a key? The controller says, no. So you'll be asking that question in a tight loop and ask, do you have a key? Is there a key pressed? And most of the time, the answer is no. Is that okay? So what we are talking about is we are in C. Okay, so I'm borrowing this screen here. I will erase that later. You're basically using this logic. While not key pressed, do nothing. Okay? It's a tight loop. It is executing. It's using the processor 100%. Okay? It's not a problem with this particular computer, because back in those days, you do not have multitasking. You don't have multi-threading. There's no multi-anything. Okay? So what if you use up 100% of the processor time just to see if a key is pressed on the keyboard? There's no consequence. It's okay. Everything's fine. What if you are to do that today? Why is that not such a great idea today? Okay, some people have a Mac, and I can see other people with Windows and some other people with Linux in this class. Or if you think about a cell phone, okay, what would be so bad if the processor keeps polling, all the devices and say, do you have something for me? So it will basically just go in a circle. It will first ask the touch screen and say, did the end user touch anywhere on the screen? No. Then it will go ask the buttons, right? And say, is one of these buttons pressed? No. Then it will ask the Wi-Fi controller and ask, did you just receive a packet? No. Then it will ask the cell radio and ask, did you receive a packet? No. Then it will ask the microphone and say, did you receive anything? No. And so on. And after that whole sequence of questions, then it'll go back and ask everything again. Why would that be not such a great idea? It uses a lot of processing power. What if you're playing a video game, okay? What if you're playing a video game? I know most of you have games on your phones, okay? I have one too. So let's say you're in a game, right? And there are times you're not pressing anything on the screen, right? The game is going, the animation's going on, and the phone decides, I'm going to use the tight loop that I just talked about to figure out whether a device needs attention. What do you think is going to happen to your game? It won't be doing anything, right? Because it's going to burn up all the processing power just for asking the I/O devices, do you have something for me to process? That is not such a great idea. So what do we need? Interrupts. Okay? So we need the concept of interrupts. I'll give you another analogy. Some of you have been to my office, right? You have been to the office of some professor, right? At some point of your life, I hope. Okay? So do you think the professor, would do the polling method and constantly ask, is there someone outside of my office? And keep asking the question, or keep looking out of the office and see and try to say, oh, do I have a student? Do I have a student? Do I have a student? No, the professor will be playing his own video games, right? Until you walk in, and then you won't get noticed, and then you have to kind of like, professor. Then the professor go like, oh, okay, hold on a second, let me pause my game, right? That is interrupt. That is interrupt, because you are interrupting the professor to get the professor's attention, okay? The professor definitely has his or her things to do when you are not present. Is that okay? Now, why is that concept related to the stack? Well, let me ask you this question. So let's say you walk into my office, and I'm playing a video game that can be paused, okay? So you come in, I go like, oh, definitely, I'm going to answer your question first. So I'm responding to an interrupt. I'm surfacing an interrupt. That's the technical term is surfacing an interrupt. So I'm surfacing the interrupt, and then I'll look at your question, I'll answer your question and whatnot. And let's just say that after 5 minutes, you say, okay, I think the issue is addressed, I'm good, and then you leave, right? After you leave, what do you think I am going to do? I'm going to go back to my game and unpause it and continue to play my game, right? Now, the biggest question is, how do I remember to do that? So let me repose the question. You walk into my office, you go like, like that, okay? What do you think the first thing is, what is the first thing that I should do? I will write down on a piece of paper and say, I was playing a video game, put it on the monitor, okay? Then I will go ahead and answer your question, right? When you're done, then I go back to the screen and go like, what was I doing before the student walked in? Right, I was playing the video game. Then I go back to the video game on the computer, unpause it, and continue my video game. Does that make sense? Okay. What do you think that slip of paper is equivalent to? Where is on the computer is equivalent to that piece of paper? The stack. Okay. So the computer, this computer, okay, if it's interrupt driven, it has got its own thing to do, okay, in the background all the time. It's using all the processing power. It could be decrypting some kind of packet. It could be trying to crack some encryption and whatnot. I don't know what it's doing in the background, okay? When you press the key on the keyboard, what's going to happen is the keyboard controller is responsible to scan the keyboard and figure out that, oh, okay, the return key has just been pressed. The keyboard controller has no idea what it means when the return key is pressed. All it wants to do is to tell the processor and go like, hey, we got a key, somebody process it, right? It's kind of the same thing as you walking into my office and go like, like that. So what's going to happen right at that moment is the processor will push the address of the next opcode to execute on the stack. Okay? Remember, the process is always executing something. The program counter always has a particular value that says, oh, that is going to be the next opcode that I need to fetch. That's going to be the next opcode I need to fetch. Suddenly, the interrupt happens. So what the processor is going to do is to say, okay, let me keep track of that. Whatever the program counter is, I'm going to push it on the stack first. Okay? Then it will go to a particular special place where a very special subroutine is. That special subroutine, in this particular case, is the one that is responsible to process a key press on the keyboard. Okay? So that particular subroutine will go through a lot of stuff. They'll go to the keyboard controller, ask, okay, what is the key code? Okay, this is the key code. And then it will stuff it into a buffer, and then it will try to raise a flag and say, hey, operating system, you got a key to process when you get to it. And then the interrupt surface routine is done. When the interrupt surface routine is done, what do you think it should do? It goes to the stack, right? And then on the stack, it will retrieve what the program counter was before the interrupt. Then it will get back to where it left off before the interrupt happened and continue execution at that point. So is that concept okay? Is that okay? All right. So when you're pushing, when the interrupt happens, all that pushing is not done in instructions, it's done by hardware. So somewhere in the hardware of the processor, it knows how to do that. But now the question is, since it's also using the stack, right? What if you do something like this? What if you do something like this, and the interrupt is to happen between line 10 and line 11? What is going to happen? Or what is, oh, okay, I take this back because, okay, so later on, so let's say we do it this way, and then we just say add AA, and then we decrease the stack pointer again so it points back to the return address. And then we can do the usual subroutine exit, which is LDB D, increment D again, and then JMPB. Okay, so we'll do it this way, which works in the processor that we have because it has no interrupt mechanism. But assuming that it has an interrupt mechanism, and the interrupt is to happen right at this point. Okay, so assume that we have an interrupt happening here. What is going to happen here? What is going to happen to the stack? What is going to happen to the stack pointer? Remind me again what happens when the interrupt happens. How can the processor remember where to get back to? It saves the return address on the stack, right? On the same stack that you are using, okay? So when the interrupt happens, what's going to happen, which is not specified by instructions, okay? So this is not done in hardware, not instructions by the processor, is going to be the following. So it's going to say, oh, I need one space on the stack, decrement the D pointer or decrement the stack pointer, And then it's going to store into whatever the the stack pointer is pointing to, the current PC. Now, this is not a valid instruction, so don't even try to do it. But this is what it's going to do. The processor is going to do this. It is equivalent to what I'm displaying here. Is that okay? What is going to happen to your actual return address for the subroutine? It's going to be clobbered. It's going to be overwritten. But do you know about it as a subroutine? No, you do not know about it because all of this stuff is happening behind your back. So when the interrupt is done, okay, when the interrupt is done, it's going to do the reverse, which is LD, PC from D, and then it will increment the stack pointer again. Then your code will continue to this point here. But guess what? Even though the stack pointer is maintained, when all of this stuff is happening, what the stack pointer was pointing to, or what is below the stack pointer, is not there anymore. Decrement, okay, no content is changed. Store to whatever D is pointing to, the program counter, that clobbers your own return address. That is why you do not do it this way. You do not mess around with the stack pointer. You can decrease it, that's fine. But you do not increase it unless you know that whatever it was pointing to is no longer needed. Are we doing okay so far with that concept? We can spend a little bit more time maybe later to talk about interrupts, but it's mostly just talk because unfortunately the processor that I use in this class do not have the mechanism of interrupting. Okay, so it's mostly just a concept, but it is important to get a concept in your head because there are jobs that requires you to program in assembly code for interrupts. Yep.
So if you want to make your processor able to do interrupts, you just have to add like another register.
No, it has to have a special line to the processor itself to raise an interrupt to basically cause an execution cycle to look into, okay, do we have an interrupt? Do we need to do something special? So it's going to be a fairly significant modification to the processor to do that. Okay. So are we convinced that this program is not going to work if an interrupt is to happen right at this point? Yes? Okay. So if this is not going to work, how are we going to do this? Well, the idea is don't do this. Okay? Instead of doing this, let's make a copy first. CPR is copy register, where register C is now the same as register D. Now that we have register C being the same as register D, then we can use register C to get to what we want. So I'm going to comment in this one, every single line here. So now C is also the address of the return address, or it's the address of the return address. That is correct. Now C is the address of X, and at this point A is dereferencing the address of X, which means it is just X, right? And once we have X, we can double it. So A is now 2 of X, which is the return value. So at this point, I'm just going to get rid of this stuff here, or I can at least copy and paste it to somewhere that is not important. Okay, there we go. Then we can do the usual return code. This decrement D is not supposed to be there. There we go. Yep.
Oh, where you put 2x, did you mean to put ampersand?
Say again?
So where you put 2x, did you mean to put ampersand?
No, that's actually 2 times X. Not ampersand, I was just using the shorthand of multiplication. All right, so do we have any questions from line 10 to line 13? Because line 14 to 16 is the same as before, that's just returning to the caller. So the only new stuff that we are doing here in double is how do we get to the parameter? Okay, so let's start with line 8, okay, the comment of line 8. Do we have any questions about that line? The parameter is 1 byte on top of where the stack pointer is pointing to. Do we have any questions about that? No questions? Okay. Line 9, the stack pointer is pointing to the return address itself. That's basically the agreement between the caller and the subroutine being called. Yep.
What if between parameter and return address is like they're not
Consecutive?
consecutive, right? They're not like
It has to be consecutive. They have to be consecutive. So how you place the parameter and where the return address is located, that has to be agreed upon between the caller and the callee. And the usual agreement is they have to be consecutive. Okay, so we don't have any questions between line 8 and line 9? Is that stuff all good? Let's look at line 10. Line 10 doesn't do anything too exciting, does it? All it does is to make a copy of the stack pointer into register C. So now register C and register D both point to the return address, which is not what we want, right? We want parameter X. On line 11, by incrementing C, D stays put, okay? This whole time, D stays put. I'm only incrementing register C, which has no special meaning anywhere, so that it can now point to it is now pointing to X, or it has the address of X, just different ways of saying the same thing. Are we okay with that? Are we okay with line 11? Is everyone convinced that after line 11, register C has the address of parameter X? Are we good? Okay. Line 12, okay. Well, since register C has the address of parameter X, dereferencing C is going to get to the value of parameter X. Is that okay? And we just put it into register A. Do we have any questions about line 12? How we get to the value of the parameter? No questions? Okay. Any questions about line 13? This is the quickest and easiest way to double the value of register A, adding A to itself. So is that okay? All right. And then line 14 to line 16 are identical to what we had in the previous function. So it's just saying, okay, the stack pointer is pointing to the return address. Good. Grab that return address, put it into register B, increment D because we don't need that anymore. And then we jump B to continue execution in the caller. Are we good? Yep.
Should we increment D one more time since we don't need parameter X?
Aha, that's a good question. The question was, should we also increment D one more time because the parameter is still sitting on the stack? The answer is no. The answer is it is the caller's own responsibility to deallocate the parameter. Okay? Now, I understand why you have that question because, well, it seems like the subroutine knows how many parameters there are, so why don't we let the subroutine do the deallocation also with the parameters? Why just the return address? Okay? So that's a very good question. So to answer that question, we're going to go for another digression. You guys like digressions, don't you? Some of you. Okay, so we'll do this one here. Okay, we'll say sum until 0. uint 8 underscore t. We call this x, comma, dot, dot, dot. Okay. Well, first we look at the prototype and go like, Tack, is that your own syntax? No. It's not my own syntax. C actually does allow this particular syntax. Okay? Then what does it mean when we say comma and then dot, dot, dot? It means we have a variable number of parameters. When we say variable, what do you mean by variable? I mean any number. Okay? So dot, dot, dot can be 0, can be 1, can be 20. I have no idea how many. Is that okay? So this is actually legitimate C and C++ syntax. It is unlikely that you have seen this in cisp310. I'm not making that assumption. But I'm pointing it out because this is why we set up the stack the way we set up the stack. Okay? So if you have something like this, then how do we make use of those extra arguments? Yes?
Out of curiosity, you said there's like an unlimited amount of parameters. Are they all the same type?
We do not even know the types.
Wow, okay.
So that even the type is not known. Now, which crazy function makes use of something like this? Printf. How many people know what printf is? Okay, a few. Okay, very good. Okay, so of the few who has done printf, what is the first argument to printf? It's a format string, right? And inside the format string, what can we have? We have literal stuff that we can just print. But what else can we have inside the format string of printf? Placeholders, right? So depending on how many placeholders and depending on how the placeholders are specified, we can be specifying an integer, we can be specifying a pointer, we can be specifying a string, we can specifying a long, a short, and so on and so forth, right? So that becomes your variable number of arguments. We don't even know what they are. Okay? The format string itself gives you a clue, gives the subroutine a clue of what to expect after that. Okay? But in this case, let's just say that we have a whole bunch of numbers. Okay? So I'm going to give you the code here, and then we can look into this and translate it into assembly too. But that may be a little bit too much. We'll see what to do here. So the first thing what I'll do is I'm going to have a local variable. Okay, we'll say p is a pointer. Okay, and p is initialized to x, the address of x. And what I'll do is I'll just say that if whatever p is pointing to is non-zero, I'm going to continue with this loop here, and I have to maintain a sum. So I'm going to say uint8 underscore ts, which is our sum, and sum is initialized to 0. And in this loop here, all we're going to do is to say sum is sum plus, or sum plus equal to, whatever p is pointing to, and then increment p, so that it points to the next thing. Return s, which is the sum. That is how we use a variable number argument type of function. Is that okay? So how do we call this? Okay, so look at it from the caller's perspective. So from the caller's perspective, okay, let's say we have an imagine main here, okay, uint8 underscore t. Let's call that I don't know, I. Okay, so I can now say I equals to sum until 0, 1, 2, 3, 4, 5, 6, and then the 0. Yep.
So is that kind of like an array then, since they're stored sequentially?
Say that one more time.
Is the variable number of arguments, is it kind of like an array?
It is not an array, because when you say an array, it means everything has the same type. But it doesn't have to be the same type in this case. So it's all up to the logic of the subroutine to figure out, how should I interpret the other arguments. So typically, it is an assumption of everything being the same type, like in this case, or in the case of printf, the first argument would have some indication of what should be following. But if you do not give it what is supposed to be following, the subroutine doesn't know. It would just do something wrong. So is that okay? I mean, is this illustrating the necessity of only the caller can clean up the arguments because the subroutine does not know how many arguments there are? But in this case, you can say, oh, but clearly we know that we have 1, 2, 3, 4, 5, 6, 7. We have 7 arguments on the stack. Why can't we just use the 0, which is the no terminator, as an indicator so that the subroutine can also clean up the stack? Well, let me ask you this question. What if I do something like that? I can do something like this, right? So if I do something like this, there are actually this many arguments on the stack. But if you ask the subroutine to say, oh, use the no termination to determine how many things you have to deallocate on the stack, it will only deallocate up to here. It doesn't know there are these extra 4 arguments on the stack as well. So once again, we cannot rely on the subroutine itself to deallocate the arguments. it has to be the caller who is deallocating the arguments. Is that okay? So some of the conventions that we use in this class has to do with conventions of C. Are we good? Okay, all right. So getting back to our original code, okay, so let's go ahead and finish this, and we'll have our main, okay. And inside main, we're gonna have a, let's see, what should I have here? And I don't want to use the, well, we could use the same name here. And then we say x equals to, I'm just looking at the time, so I can determine the complexity of the example. The return value of 5 and 7. Okay, there we go. Okay, so this is our main. In assembly code, how are we going to code this main? That becomes the next question. Okay, main is a entry point, okay? What is the first thing I need to do? Well, we got a local variable. Where do you think that local variable is? It's a local, auto-local variable. Where does it live? Lives on the stack. Very good. So the very first thing we do is we allocate a space for this on the stack for the local variable. Okay, so we allocate for local variable x. And then we can move on to line 15. We can actually try to set up the call. Oh, we got 2 arguments now. Oh, that won't work, would it? Because double is supposed to only expecting 1 argument. So we'll just do it with 1. So we get rid of 7 here. Because otherwise it becomes a compile time error. There we go. Okay. So we have to, what should I do now? I got 3 things to do on line 15. I got an assignment, I got a call to double, and I also have a call to 5. Which one of the 5 should I do first? Well, can I do the assignment right now, like right away? Do I know what value to use to change x? Right now, at this point, on line 20. No. Do I know what I need to use as an argument to call double? Right now, on line 20. Nope. No, we don't. So what do we need to do first? Call 5, okay? So we need to call 5 first. 5 is easy to call, okay? So we'll say LDI A with main return from, I'm just making it really long so that we know what the label is. Return from 5. Decrement D again, allocate for return address, and then we store A to where D is pointing to on the stack. Then we can just do a JMP to 5. Okay, this is how we call 5, and then the label, which is main return from 5, is here, because this is where I want to continue execution when 5 is done. Does that make sense? Because main underscore return from 5 as a label is my return address. It's just a symbolic name of the return address. It specifies when 5 as a subroutine is done, where do I want it to continue execution? Well, I want it to continue on line 25, whatever I specify on line 25. Is that okay? What do I have on line 25? Remember, 5 is not a void function. It does return the value. What does it return? It returns the value of 5. And how should I use that return value? If you look at the C code on line 15, how should I use the return value of 5? I have to use it to call double, right? So I have to use whatever the value is returned from 5 as an argument to call double. Is that okay? Where do I put arguments? On the stack. Is it on the stack right now? No. Where is it now? It's in register A. Okay, by convention, it is in register A, but it is not in any memory location. It's not on the stack just yet. So what should I do to put it on the stack? What is the first thing I need to do if I want to put something on the stack? Huh? Allocate. So how do I allocate something on the stack? Decrement the stack pointer. Okay, I move the bookmark first to say that this page is now reserved. Don't touch it. Okay, so I decrement D to reserve for argument to call double. Okay, well, once I reserve it, I can put something there. So I can now put, what should I put there? Register A. Oh, tell me again what is in A now? I mean, I don't seem to recall. I mean, isn't A still the same thing as main underscore return from 5? No, because it is coming back from the subroutine. The subroutine has already put the constant 5 in register A. So at this point, register A has the constant of 5. Is that okay? Okay. Then what else do we need to do? I want to call a subroutine, right? I'm done with pushing the argument on the stack. What else do I need to do? I still need to push the return address on the stack. Okay. So, well, we'll do that. So this time I will call this main return from double. Decrement D again. Reserve for return address. Store onto the stack itself. Unconditional branch to double. And here is main return from double. Okay, so I call double, double says, okay, I know what to do, put the value, twice the value of the argument in register A, and then continue on line 32 when it comes back. What do I need to do now? If you look at line 15 of the C code, what else do I need to do at this point? I need to store the return value into local variable x, right? Okay. Well, before we do that, we got one extra thing to do. What is still sitting on the stack right now? There are two things on the stack right now. One is the local variable. What is the other one? The argument of double. Because why? Because remember, it is the caller's responsibility to deallocate the argument. So as the caller, main, has to deallocate that argument. So it has to do an increment D to deallocate the argument to double, because it's still sitting on the stack right now. Are we good so far? Okay, remind me again, why is it the responsibility of the caller and not the responsibility of the subroutine to deallocate the arguments? Yeah, exactly, because the subroutine does not know the number of arguments actually pushed. And that has to do with the variable number of arguments, construct in C++, C and C++. Okay, so now that I have incremented D, what is D pointing to at this point? There's only one thing left on the stack. So that has to be whatever the D register is pointing to. What is on the stack right now? The local variable x. D is pointing to it, right? If you look at line 15, what am I supposed to store into local variable x? The return value of double, right? Where is that? Sorry? A. Register A, very good. How convenient. Because register D is pointing to local variable x, and then A has the return value from double. So all I have to do is to say, hey, store register A to wherever register D is pointing to. And that's the end. So technically speaking, okay, I need to deallocate x, which is a local variable, at the very end of main. Now main cannot return because it is not called from anywhere in assembly code. So the best I can do is halt. Okay, that's the best I can do in assembly code. So to make this program runnable, we still need one little thing at the very beginning of the program. Because if I don't do this, then it will start to execute line 4. The program starts with line 4, which is not what it's supposed to do. It's supposed to go to main first, right? And the second thing is the stack pointer is not initialized. So I have two things to do. Technically speaking, I should initialize D to 0, which is the way we initialize the stack pointer. Yes, you can argue and say that, well, isn't all the registers reset to 0, at the beginning of the execution of the whole thing? The answer is yes, okay? But I'm making a point here to make sure that we do initialize the stack pointer to something. And then we just do an unconditional branch to main to continue execution in main. So main is not really called, it is just jump into, and it has no place to return to. Yep. Yep. Oops. That one. Okay. All right. So this is going to be kind of what you'll be doing with the homework assignment or the lab activity today. And before you leave, I know some of you want to know this. Yep, what is the passcode? That's the most important question. Okay, so let me set up the time first. Frame. So the passcode is frame, F-R-A-M-E, frame, okay? Not warframe, just frame. And I'm going to set up the due date to April 30th. Yep.
I just want to let you know on Thursday I won't be in class because I'm heading to Washington for a funeral.
Okay. All right.
Do you have a lab on Thursday?
On Thursday? I might. Okay. So the lab is up, it should be active now.